Welcome all. Thank you all for coming to this public lecture by Professor Leo Kouwenhoven. It is our great pleasure to have Professor Leo Kouwenhoven with us here. Leo got his PhD in Delft University. His PhD in mesoscopic physics, very specific, in 1992. And then he went to Berkeley. He spent 2 years at Berkeley as a postdoc. And then he moved back to Netherlands and worked as an academic researcher. And in 1999, he returned to Delft University and became a professor of physics. So Leo is a leader in the field of nanotechnology. I think he published many great works. And his total citation, I think, is beyond 50,000. Really? If you check Google. And so he has many awards. He was elected a member of Netherlands Academy of Technology and Innovation, a member of Royal Netherlands Academy of Arts and Science, and a member of Royal Dutch Society of Sciences. I think he got all the highest awards in Netherlands. And so now he's a professor at Delft University, but at the same time, he's the principal researcher by Microsoft Research in year 2016. So, and his more recent research interest is on the finding of Majorana fermions and use them as topological qubits. So he's the leading experimentalist in this area. So let's welcome Leo.
Thank you, Vic. That was a very nice introduction. I feel very excited to be here. It's always my second time in Hong Kong, which is fun and interesting. But it's also exciting because of the title of the slide that I put up here, Welcome to the Quantum Age, because I think it is an exciting time. We are transitioning to a new era where we can use and explore quantum technologies. So that's the topic of my presentation today. And I would like to start with a little movie that we made at Microsoft that should capture the enthusiasm about quantum.
Talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We can attack global warming.
Security.
What are the boundaries of machine learning?
Fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast, and we're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in 1 billion parallel universes at the same time?
Well, that shows something, right? I was actually also filmed for this movie, but I didn't make the final cut. I guess my words were not as enthusiastic as those from my colleagues. You saw Charlie Marcus, Michael Friedman, and Christoph Sverre acting in this final version of the movie. I do share their enthusiasm. I think we are starting something that is really, changing. It is. I would not only say it's revolutionary, but it's also a change in our paradigm of how we treat science and technology. So to actually do something, to make the technology that will allow us to use quantum mechanics as a resource for computation, what Microsoft has done is build a global team. And it's a very nice new model of bringing Microsoft labs at university campuses. You see several key people in the team, people who are spread around the world. For instance, in Redmond, the headquarters at Microsoft, we have the Quark software team headed by Christa Svøre, and also the engineering team headed by Doug Carmine. If we go east, or actually a little bit south first, Santa Barbara, we have the theoretical physicists group headed by Michael Friedman and Chetan Nayak. Then we go east to Delft, where I'm the director of the Station Q in Delft at the Technical University in Delft. Denmark, Copenhagen, we have Charlie Marcus as the director. In Sydney, David Riley is director of the Station Q in Sydney. And here at Lafayette, we have at Purdue University, we have a material science group headed by Mike Menfra. So that's the global team working in a new model where groups of Microsoft are embedded within universities, so where they are allowed to work with students and postdocs, but at the same time can make use of the huge network that Microsoft can provide in software and in engineering. So that is our organization towards making a quantum computer. That is the goal. Our boss, Satya Nadella, is very clear about it. He sees quantum technologies as one of the three future technologies for Microsoft. There is altered reality, there is artificial intelligence, and there's quantum technologies. So what I would like to do in this presentation is, first of all, give you an introduction on quantum computing, why it is different. Then the approach that Microsoft has chosen for building a quantum computer, that is the topological approach. And look at some of the challenges, the grand challenges, that if we have this machine, we will be able to address. Now, the first notion is that quantum computing is really different from classical computing. It is really a change in paradigm. And the metaphor that I'm using for it is, let's first look at the historic view on it, where we start with the abacus, from a long time ago, where you can encode information, actually process information, by just moving these balls left to right. It's a binary system. The ball is either left and right. And that same binary system we still use in our modern chips. It's a bit more powerful, but the building blocks are still the same. And that is going to change when we have available the quantum mechanics, the laws of quantum mechanics as a resource for encoding and processing information. Now, that is really a change in paradigm. And this is my metaphor for it. Classical computer or classical IT has its limits. And even if you have the fastest bike available, and even if you go faster and faster, you will never take off. That requires a new principle. You need wings, etc. And that is what quantum IT can provide. It is built on new principles and can lead to other territories. It can take you off. So do we actually need more resources for computing? Well, if you look at the largest supercomputer, which is nowadays, or actually already for a couple of years here in China, these large supercomputing centra, they can compute the chemistry of small molecules. Like a small molecule like caffeine, the ground state can still be calculated in this supercomputing center. If you make the molecule a little bit bigger, for instance, this is actually also very interesting, an industrial relevant molecule, iron molybdenum complex, is already too large to calculate its ground state and to calculate or predict the quantum chemistry of that molecule. And I'll come back to this molecule at the very end of the presentation to illustrate that this is really a very relevant molecule for industry. And to find the answer, what is the ground state or what is the quantum chemistry of that molecule, would be a huge energy saver for all of us. So that's why we need a quantum computer. The classical computers that we have are obviously restricted to small problems, to small chemistry problems. Bigger chemistry problems are impossible to calculate with any classical computer we can even think of making also in the future. So what is this chemistry? What is this quantum mechanics? Well, it all started 100 years ago. You see Niels Bohr, Albert Einstein. But we believe that all the chemistry that we have, even for the large molecules, are described by the Schrödinger equation. This is a very simple expression of the Schrödinger equation, but you can put a lot of detail in there with all the atoms of a larger molecule, and this equation should describe the quantum chemistry of that molecule. For small molecules, or atoms, small molecules, we can actually solve the Schrödinger equation, but as soon as it gets a little bit bigger, for instance, in this example of this iron-molybdenum complex, it's too complex. It takes an infinite amount of time to actually solve the quantum chemistry. So the motivation from Einstein and Bohr to think about quantum mechanics and to come up with its principles was to understand nature, to come up with a description of phenomena occurring around us. And the principles that they had to assume as assumptions in this quantum theory were weird, counterintuitive, very hard to accept principles. That led, even 50 years later, this quote from Richard Feynman is that at that time, 50 years after the inventions from Einstein and Bohr and Schrödinger and others, that he thinks he can still safely say that nobody understands quantum mechanics. If you think about the deeper philosophy of quantum mechanics, then you can try to understand one aspect of it, but you always end up with some strange construction. For instance, you heard Charlie Marcus say in the little movie that a quantum computer is actually computing in 1 billion universes. So that's one of the ideas that people have in order to get a grasp or get an understanding of quantum mechanics. To me, that sounds still weird. Okay, the motivation for Einstein and Bohr is to understand nature, to describe nature, and that includes why is grass green or why is a leaf green. And we need quantum to actually calculate these properties of that we see around us in nature, whether it's the color coming out of a piece of material, or the chemistry, or so many other things. Now we've changed also our point of view a little bit because we know that quantum mechanics rules the chemistry in nature. We can also say that with a slightly different point of view, but still saying the same thing, is that nature is actually itself a computer, and it computes according to the rules of quantum mechanics. It's just a different point of view describing the same thing. And it's interesting because if nature can do it, then so should we be able to do it. There's proof of principle. If nature can compute using quantum mechanics, then there's proof of principle. We should be able to build a quantum computer. The same motivation was there 100 years ago when people started to make an airplane. They knew birds could fly, so there was proof of principle, and you only had to find the right material and construction to build a flying object. So we want to enter a new era, let's say quantum 2.0, where we're no longer using the Schrödinger equation to describe nature, but instead we're using the principles of quantum information processing to describe nature, but also to create new quantum technologies. And we, or at least I am, some of you are, but also theorists, but I'm an engineer, and we want to build these things. Not get stuck on the understanding of the fundamental philosophy, the fundamental principles, but just go ahead and start building those systems. There's a famous quote from, again, Feynman. Feynman is a key feature in my story. Famous quote is that don't keep thinking about these arguments between Einstein and Bohr on the principles of quantum mechanics, whether it's a true theory or not. Just shut up and calculate. Feynman said. And we've changed that slogan into shut up and engineer, make it. Now, why did Einstein and Bohr actually invented quantum mechanics? Well, for instance, to understand the properties and the behavior of atoms. And atoms, how they bind into molecules. And here we have a very simple molecule, two atoms connected by two lines. For instance, oxygen with a covalent bond in between. And the way these two atoms are being held together is by the fact that they share an electron. And this electron doesn't sit simply in the middle of it, doesn't jump back and forth between the two atoms. It actually goes into a superposition, what we call a superposition, of being at two different positions at the same time. So it sits on both oxygen atoms at the same time. And that superposition holds together the two oxygen atoms. Now you maybe remember those pictures from chemistry classrooms. This is methane, where the little sticks, in fact, are that actually hold the atoms together, are actually electrons that sit at the same time on these different atoms. And the little sticks are actually superpositions that form the glue that keeps atoms together into molecules. Now this is, all atomic stuff, very small and not very real life, not our world. But we can make these things bigger, and that has been our drive in the past 20 years. Can we make objects that are bigger and bigger, much larger than single atoms, but still behave in this quantum mechanical fashion, and still have superpositions in it? And we've been building boxes for electrons, little boxes that are so small that they can only hold a single electron at most. And for instance, if you take a configuration with just two boxes and put in one electron, then if the electron sits in the left box, we can actually call it a bit. And we can define this configuration as a bit. Let's call it bit 0. Equally, if the electron sits in the right box, then we can call it a bit 1. One electron shared in two boxes can encode this single bit. Quantum mechanically, if we make a little connection, a tunnel connection actually between these two boxes, the electron will go into a superposition of being in the left and right box at the same time, encodes a qubit. Encodes a qubit in the sense that it encodes a 0 and 1 at the same time. It's a superposition of these two bits. A little bit more formal, the way we describe is that this superposition, being in the left and the right box at the same time, is a superposition of these two quantum states, the 0 bit and the 1 state, and the 1 bit at the same time. So it's happening simultaneously with these two prefactors. There's also a graphical representation, this little sphere, where on the north pole we have bit 0 and bit 1, and this particular superposition where when alpha equals beta occurs at the equator, but in principle all other points on this sphere can be reached in a superposition. So it's a little bit like, it's not just 0 and 1, but it's everything in between as well at the same time. So it's the quantum version of an analog computer. So we're actually going back to analog computers, but now the quantum version of it. So why is this useful? Why is it useful for computing that you can have a superposition? So let's have a little, before we dive deeper into say quantum computing, let's have a preview why this could be useful. And we can take the example of solving the labyrinth. What a classical computer does is pretty much the same as what we do. We just take path by path, try path by path sequentially until we find the exit. The nice thing about the labyrinth problem is that as soon as you have found the exit, you know immediately that you have found the right solution. Quantum mechanically, the system goes into a superposition and all paths are taken simultaneously. Again, with the nice feature for this labyrinth problem, that if you find the right solution, you know you're done. You know you're out and you know the right solution. So the key difference between classical computing and quantum computing is that classically, you do everything sequentially, and quantum mechanically, you can do it in parallel by making use of superpositions. Now, how can we, I already mentioned these boxes that can have single electrons where the electron sits in the left or the right box. What kind of hardware approaches are people actually pursuing at this very moment? And I think this list of 6 different approaches are the key or the main approaches out there. Linear optics, you can use photons and make photons interfere and actually do, if you mix it up with smart measurements, you can actually do computations. Maybe a little bit more advanced, I would say, is that if you take a single atom, ionize it, so it becomes an ion, and look at the electronic states on that atom, when it's trapped, so it's actually held in vacuum by shining lasers and creating some ferrometric pattern that holds the ion. And the electron on that ion can be in different quantum mechanical orbits, and these can serve as your quantum states, as your qubit states, very similar as these electrons sitting in the left or right box at the same time. So that's the approach of ion traps. Now, I would say this approach was basically the first approach where people could demonstrate the principles of quantum computing. The first quantum gates or the first 2-qubit gates, or where you actually create superposition states between different objects, etc., were all demonstrated using ion traps. And I think at the moment they're studying like somewhere between 10 and 20 of these ions at the same time. Actually, to hold them in a small pocket in vacuum, you need a big machine. The vacuum machines that people have and the lasers that people use for ion traps are actually huge, gigantic. And it doesn't scale very nicely. If you go to 100 qubits, you need the size of this campus to hold all these electrons in the right spot. So the same principles, but you're actually using a solid to hold ions, is done in these what's called the NV centers. In diamond material, so carbon material, some of the defects, and in particular these NV, nitrogen vacancies, in diamond, are very similar as ion traps. But in this case, the ions are trapped in solid state, in diamond, where you can actually put them at particular locations, and you can also address them on a much finer and smaller length scale. Again, addressing them with photons. Then the approach that actually I was involved in myself in the 90s and also in about 2005 or so, where we create these quantum boxes that can store single electrons. And you can demonstrate that the electron in the left box is a bit, right box is a bit, and you can make superpositions and everything. And this is the approach where initially the location of the electron was used as the basis for the bits. And now people have actually changed to the electron spin. That is also, every electron has a spin. If you put an electron in the left box, then there's also a spin in the left box. And you can use the spin degree of freedom to create qubits. This is a very successful approach. And in particular, Intel is pursuing this to scaling it up to larger and larger numbers. Then there's superconductors. Whereas all these other approaches make use of individual particles, individual electrons, individual vacancies or photons, in superconductors, it's a different beast. In this case, there are currents flowing counterclockwise and clockwise that form the qubit state. And you really make use of the properties of superconductivity, so absence of dissipation, and you already have a quantum ground state, that allows you to use a collective state with many particles involved as your individual quantum state that defines the qubits. People didn't believe this would work until it was demonstrated. People did not believe that you can view a superconductor as a system where you can have individual quantum degrees of freedom that you can use for qubits. No theorists believed it until it was demonstrated experimentally. It's one of those examples where really you had to counterprove the general belief in order to go forward. And now this is the most popular approach for quantum computing. Google, IBM, and many groups around the world make use of superconductivity to build larger and larger qubit systems. Last but not least is the topological approach that we are pursuing at Microsoft, which actually has a combination of superconductivity as well as electrons and quantum states that are confined somewhere. That's the combination of it. And I will say more about this later. Now, the difficulty, the challenge, or the problem of these approaches is that you have an individual particle that you're using to define your qubit. For instance, if you take a single electron, it has a charge, it has a spin, and that electron sits in an environment where there are also other electrons and other spins. And they're all interacting a little bit with each other, maybe some kind of weak interaction, such that the magnetic moment of this spin couples to the other magnetic moments, and they're all exchanging a little bit their degrees of freedom. Or in a, let's use a quantum information description, the information that you've stored on this particular qubit is leaking out very quickly into all the other degrees of freedom in the system. One approach is to make this interaction with the other spins as small as possible, to isolate it, to put it as an ion in vacuum and have no interactions with whatsoever. The opposite approach is to make the interaction actually very, very strong, and to, as if you lock them together in a collective state. The Greek dancers, those guys in the middle, are no longer free to move around by themselves. They're locked to their neighbor. Only the guys at the very end, in particular this one, can make these funny jumps. Still has some freedom of motion. So can we do something similar where we lock the degrees of freedom in the entire system, only at the endpoints we have some freedom? And so we will be using this inert state as something that holds everything together. And the only degrees of freedom are in the left and right end state, where we can store information. And we want to do that in a particular manner. Now, these ideas of making collective states resonate very well with the conference and the workshop where we are this week. Topological phases, Nobel Prize last year, with the citation that these three people, Thouless, Haldane, and Kosterlitz, got the Nobel Prize for their contributions to the theoretical discoveries of topological phase transitions and topological phases of matter. And the prime example that we always use to explain topology is that a coffee cup is the same as a donut, because you can gradually deform the coffee cup without breaking any pieces of matter, just gradually transforming them into a donut. Now, you don't know, if you just look locally at the coffee cup, you don't know its topology. You don't know whether it has the same topology as a donut. You really have to look at the entire object, at the collective state, the global state of the cup, to know its topological property and to know that it's equal to a donut. The measurement of a local, where you have a local interaction with a local point, doesn't tell you anything about the topology of the system. It's a global property. Now, to use topology for information, mostly information memory, was surprisingly already invented 500 years ago by the Incas, where we in Europe and probably in the US, we were still, writing things on a blackboard to keep count of things. The Incas were making knots in ropes, writing complete stories in knots in ropes. They could store them for a long time and retrieving them and still read out the same information. It's a remarkable story that by nodding, you can actually write stories in topology. Now, this is classical encoding, topological encoding of information. For doing the quantum version of it, we have to make a jump from the Incas to Italy, and in particular to Ettore Majorana. A key feature for topological quantum computing is the particle that Ettore Majorana predicted in 1937, and that we've all been looking for, the physics community has been looking for, until we found some signatures about 5 years ago. And some signatures that this Majorana fermion indeed exists. And the ideas of Majorana, there are several versions of it, but I want to focus on the version in condensed matter systems, where we use material to actually not just find the Majorana fermion, but to make the material such that the Majorana fermion has to emerge by design. And the idea is the following, and we actually go back to the Greek dancers, where we lock all the degrees of freedom except one of them. And this row of electrons where all the seeds are taken except, let's say, one seed at the end is still free. It's almost completely locked. And if everybody would just move over by one seed, then the whole row effectively moves the whole row moving over one seed moves the whole over to the entire other end. And this you can do again and again, actually. And quantum mechanically, each person will go into a superposition of between two seeds, but effectively the whole goes into a superposition of two seeds, but these two seeds are now separated by a long distance. And that's actually a remarkable superposition, because it's a superposition where this one empty seed has now been broken into two empty seeds, sort of two seeds that are half filled, half empty, at the opposite ends of the row. And slightly different language says that the presence of an electron here is equal to the absence of that electron. Or in particle words, particle equals antiparticle. The particle that sits here is described by half an electron and half a hole at the same time. Or in other words, as Majorana defined as a symmetry relation for his particle, particle equals antiparticle. Sometimes this is called electron fractionalization, or in fact it is a superposition of the whole being at these two opposite ends of the row at the same time. Now it's kind of interesting because this particle-antiparticle symmetry immediately tells you that this state, or this quantum state, cannot have any energy, because otherwise the antiparticle would have the negative energy. It cannot have any charge, otherwise the antiparticle would have the opposite charge, and it cannot have any spin. And so all these properties are a bunch of zeros that defines the particle. So we will actually have to measure those zeros to be able to identify the presence of a Majorana. Now there's another reason why this particle is so special, and it really forms a special class of particles in the universe, because so far we only know, or we divide the available elementary particles, and also actually the collective particles as well, as either being bosons or fermions. And the way we can actually identify whether we have a boson or a fermion is if we have two of them and we exchange their positions, then nothing happens to the boson state, but the fermions get a minus sign. If you do it once more, so you change it once and you go back to the initial position, then you do it twice, then this minus sign actually again drops out, so you go back to the same state. Yeah? All particles in the universe can be divided in these two boxes. They're either bosons or fermions. Now, in a two-dimensional universe, there's an extra option. There's an extra option, and the option that we are particularly interested in is actually also true for the Majorana fermions, is that if you put the particle around another particle and bring it back to its same position, you don't go to the same state. No, instead you go to a different state. Yeah? So going back to the initial position doesn't return the state to the same state. And in fact, you have to do it for Majorana fermions. You have to do it twice to return to the same state. And these intermediate states are very interesting to encode and process information. The statistics is no longer fermion statistics or boson statistics. It's called non-abelian statistics. It actually also matters whether you go clockwise or anti-clockwise around other particles. So we take these Majoranas and treat them as a function of time. So this is the time axis now. And we start off with A and B forming one fermion, two Majoranas coming from a single fermion, and C and D, which originate from a second fermion. So we have two fermions split out in four Majoranas. Now B, that originally was connected to its partner A, and for instance C, originally connected to partner D, we can actually exchange them between this input and output as a function of time. Yeah, so what we do is we just change their positions, and we've exchanged B and C. And this is, the more you think about it, the more special this situation is, because originally B was a part of the fermion, the element, let's say the particle AB, and I now move it over to the lower end where it forms a new particle with D. Yeah, so you take a fermion, break it into pieces, and you let it combine with another partner. And this process of exchanging B and C is what we call braiding topological qubits. And for one braid, it's not so simple, it's not so impressive. But if you do a bunch of them, you start to form a braiding pattern. Now, why this is topological, you can actually see fairly quickly, because it doesn't really matter where exactly you make these braids. The output will not be influenced under some conditions, but the output will be the same, independent of the exact positions of the braids, and even if it's shaking a little bit. The whole shaking or interaction with, let's say, the rest of the world doesn't really change the outcome. Now, this looks very classical, balls that change their position, but there's a quantum version of it where if you make an exchange between two Majoranas, you actually create superposition and you create entanglement. And that will be also seen in the output on the right. Okay, so I taught a Majorana prediction 1937. In the cosmos, we still believe that these particles should exist. The neutrinos could actually be Majoranas. And in the condensed matter system, we've been looking for it since about the year 2000. And in 2012, our group in Delft had the first glimpse at it. And this was our publication in Science, making use of a solid-state device that consists of a superconductor, a normal metal, and a semiconductor. So it's the combination of those three material classes that, under the right conditions, give you these Majoranas. Now, what we did precisely, let me give you a brief impression what it looks like in real life, in the lab. So let me start this video. It is in Dutch, but you can read the subtitles.
Daarom neem ik je mee naar het lab. Hier zijn we in de cleanroom, dus kom maar mee kijken waar we die qubits aan het maken zijn. Hier zijn we in een speciale ruimte met een andere kleur licht. Eigenlijk is het heel standaard scheikunde. We hebben gewoon een vlak substraatje. Er moet een lichtgevoelige laag op aangebracht worden. We verwarmen het en die chip die wordt zelf gebakken. Hier heb ik zo'n voorbeeldchip. Dat chipje kunnen we in dit apparaat stoppen. Die gaat dan over dat chipje een bepaald patroontje schrijven. En door daar een bepaald patroontje te definiëren op de computer, kunnen we qubits maken. Dus eigenlijk hebben we nu de basispatronen, maar er moet nog wat extra's op. Je ziet hier een heel groot apparaat. En hier maken we hele fijne materialen. Eigenlijk zijn het hele dunne draadjes die veel dunner zijn dan een haar. Die nanodraadjes, zoals we ze noemen, die moeten dan op dit chipje komen om de qubit helemaal af te maken. Hier zijn we in de meethal waar we de kwantumcomputers testen. Er is wel heel veel lawaai hier en dat komt omdat we die kwantumcomputer moeten afkoelen in een grote koelkast naar hele lage temperaturen. Vlakbij het absolute nulpunt. Zo ziet de kwantumcomputer eruit. De koelkast en daarbinnen zit dan een elektronische chip met onze qubits.
One of the things got lost in translation, when I said, actually in Dutch, absolute zero temperature was translated to 0 degrees Celsius. And I wish it was true. It is a lot more complicated.
Daarom neem ik...
But these devices that we make and later give some color in your computer consist out of these different materials. Gold is a metal. Niobium tinitride is a superconductor. Then there's a semiconductor that connects the normal metal and the superconductor. You apply a magnetic field. You apply all kinds of voltages to these different electrodes down there. And then at some point, you have these Majoranas. Very briefly, these nanowires. It's different from a wafer, a semiconductor wafer, because you grow these, it's basically this grass. But this grass is extremely well controlled. It's perfect crystalline material. Diameter can be as narrow as 20 nanometers, as big as 200 nanometers, micrometers long. Different materials, and we like this type of semiconductor materials. And this fabrication in the clean room is nanofabrication, so you really process these materials on a nanometer scale. In the end, you put it in a chip. You have to make connections in the end, you're still soldering to make connections to wires. Put it in the fridge. And the fridge is not your home fridge, but a dilution refrigerator that goes all the way to 10 millikelvin. That's from 300, it's 2 orders of magnitude, 4 orders of magnitude compared to room temperature. You decrease the temperature. And of course, 0 Celsius is around right there. So it's a lot colder than 0 Celsius. So let me very briefly show you what we actually measure. These devices now, slightly different colors, but the same principle. If you measure electronic transport through the system, you see this peak. And the peak is the holy peak. If you change some parameters, for instance, on this axis, we changed the magnetic field up to 1 Tesla. And now the peak has become this red color. Or if you change the electric field by changing the voltage on a gate, again, this peak is again in red color. And we see also a plateau here. Now, if you interpret these different data sets, then we can draw a conclusion. And the conclusion is that these different data sets together actually measure this property of particle equals antiparticle. First of all, no energy. Well, these peaks now happen at 0 voltage, at 0 energy. That state does not have any energy. It only occurs at 0. No charge. In this case, we changed the electric field by changing some gate voltage. And the peak that was at 0 stays at 0. If it would be charged and you apply an electric field, the charge would change its energy rapidly. No spin. Actually, in this piece of data where we go from 0.7 to almost 1 Tesla, that change in magnetic field keeps actually the state at 0, meaning that there's no internal magnetic degree of freedom. If there would be anything, some magnetic property in that state, a spin or whatever kind of magnetic degree of freedom, it would move away from 0 if you change the magnetic field. So these 3 pieces of data tells you indeed no energy, no charge, no spin. And curiously, the fact that these resonances go to a value which is quantized in fundamental units of nature, 2e²/h, that particular value tells you that you're actually measuring this symmetry principle, particle equals antiparticle. Now, how do we know that this plateau at 2e²/h actually is a measurement of particle equals antiparticle? That's because we've been reading this paper by the organizers of the conference. So Vic and Patrick wrote this paper already in 2009, years before we started measuring those devices, that the Majorana fermion resonance should go to 2e²/h. Now, in 2012, we had the first signatures of Majoranas, but very small peaks, much smaller than the theoretically predicted 2e²/h. But just this past year, my postdoc Hao Zhang was able to clean up all the devices, make better measurements, and work together with material scientists, better material scientists, to improve the entire experiment, and we could go up to 2e² of h. Now, Hao is actually, he's not here in the audience because he's actually doing an interview. He's on the job market. He's doing an interview right now here in Hong Kong. But I'm not sure if he actually wants to leave Delft and his collaborators in Delft. He might as well want to stay in Delft. So let's go back to quantum computing. We have these Majoranas, we have the signatures, but we don't have a qubit yet. We have to make a technology out of these little peaks from Hao is a lot of extra work. And what is the motivation? I want to spend some slides on the motivation for building a quantum computer and why you increase so rapidly in computational power. Again, Feynman. Everything goes back to Feynman. Everything that we do in nano and quantum goes back to Feynman. He was always the first one to say something smart about it. And one of the things he said, thinking about computing, is that if you use the quantum resource for computing, then you could accelerate calculations. Because instead of having to act on all the pieces of information separately, if you put that information in one superposition, you only have to act on that combined quantum state. So instead of going through all the rows separately, if you can put it in a superposition, you only have to act once on that quantum state. So many things you have to do versus one thing you have to do. And in many things, it scales enormously. Let me go to 10 qubits right away. 10 qubits. If you write out all the classical states that describe 10 qubits, you need 10 kilobytes in memory. Now, the scaling works that if I add 10 qubits here in the left column, I have to multiply by 1,000 to the 2 to the power 10 in the right column. And so this, I only have to add 10, and I go 1,000 times bigger in memory needed to describe these qubits, again to 40 qubits, etc. 30 qubits you can still do on your laptop. A good laptop, not a Microsoft laptop in this case, but it's a good laptop. You can still do on 30 qubits. For 40 qubits, you need a supercomputer. 50 qubits, no, not even a supercomputer. Maybe a future supercomputer can handle it, but then it stops. This scaling is so bad that you can always add a few extra qubits that multiplies the amount of memory that you need to be able to do that calculation. That think about 230 qubits, and it would require all, or actually more than all the atoms available in the universe that you need as a memory to calculate these qubits, or to register all the pieces, classical pieces of these 230 qubits. That's amazing. 230. It's about actually 230 people could more or less in this room. That stands for, in terms of complexity, to all the atoms in the universe. Same scaling happens if you look at the time it takes to do an operation. If I do a single operation, one gate operation, an AND port or a CNOT operation, then for quantum states, you can do it in one go. But for larger amounts of classical states, it's 16 megabytes, for instance, that describe 20 qubits. It takes a millisecond on your smartphone. You can still easily do it. But then for 30, only 10 qubits extra, you need a PC. 40, you need a cloud service. 50, well, the best supercomputing center. And 60, maybe sometime in the future. But then it stops. For one gate operation, you cannot calculate anything, it's just one gate operation. So these are small numbers, and these are enormous numbers. Now, to build this technology with 50 qubits working in a coordinated fashion, without making errors, what you need is some kind of error correction. And the fact that our classical IT works so well is that error correction is very efficient in classical IT. For quantum bits or qubits or the building blocks for a quantum computer, it also matters a lot how frequently you make errors. And to illustrate that, we've made this graph. Actually, it was actually first made by the IBM people to illustrate the computational power that you can have by a particular number of qubits, given a certain rate of errors. If the rate is high, so you make errors, let's say every 1% of your gate operations, then whether you have 10 or more qubits doesn't give you more computational power. With this amount of error rate, then you cannot do much more if you make the system bigger and bigger. You only have quantum coherence or quantum coordination in pieces of the circuit, but it doesn't extend out over the entire circuit. You're not using the entire computational space to your benefits. Even if you take 10 times better or lower error rate, still doesn't help you very much. And you really have to go up to very small error rates in order, if you scale up in the number, that you also make the volume of your, let's say, your computational power bigger. You see that these circles remain more or less the same, but only if you go to very low error rates, you go up to larger and larger computational volumes. So it's super important not only to have more qubits, but it's also important to have qubits that are more reliable in order to be able to solve more complex problems. So this is actually the state of the art for the superconducting qubits, where you make one error in 1,000 operations. And you need some kind of error correction that still needs to be built in order to go to effectively go to lower rates that can increase your computational volume. So the goal or the decision at Microsoft is to not yet go towards larger numbers of qubits, but to go up on this axis and decrease the error rate. Look for fundamentally different qubits where the errors are, or the protection against errors, I should say, is actually built in the design of the qubits. And that is the idea behind using Majorana fermions and braiding operations to be protected against making errors. So that's the goal and the hope, that we reach those levels of very low error rates before scaling up to larger and larger numbers. To illustrate that good building blocks are important if you scale up to large numbers, try to make a huge structure out of cards. It's much easier to use Lego. The building blocks make a difference. What I also find an impressive illustration for scaling is that classically, if you want to have a calculation done twice as fast, you need to increase the hardware by a factor of 2. Whereas quantum, if you reach a certain level, you only have to add a single qubit to the system to increase your computational speed by a factor of 2. There's a barrier, you have to pass a certain level, but then it scales exponentially with the number of qubits in the system. So back to our problem of solving the chemistry of molecules. Classically, the time it takes to predict the quantum chemistry of a molecule increases exponentially if I increase the number of atoms. Methane, we can do, but if you go slightly larger, and I already mentioned this iron molybdenum complex, you shoot through the roof, and the roof here that people take as sort of a barrier is the age of the universe. And that makes it impractical. Now, we can make faster, bigger, and nicer computers, but it only shifts this line a little bit. The time it takes to calculate the same thing decreases a little bit, but you're still bound by the same bad scaling towards infinity. The only way to do it is to use quantum for quantum and have a quantum computer to solve the quantum chemistry of these molecules, because this scaling keeps it tractable, whereas the scaling of classical becomes intractable. So these applications of doing quantum chemistry or material science, I think, are the key most important applications that, at least at the moment, we can think of doing when we have a quantum computer. These are examples where the one that I like most, because I once started as a student to work on high-temperature superconductivity, it would be nice to bring it a little bit up to room temperature. So if we can solve or help to solve this problem, that'll be fantastic. But there are other, material science problems equally important, from toxic materials, catalyst, and for instance, this example, the catalyst for nitrogen fixation is actually one that I want to say a few extra words on. Now again, Feynman, he already said, okay, if you want to solve chemistry, quantum chemistry problems, then you need quantum. Quantum is the only proper language to keep track or make these problems tractable. I rephrase it a little bit is in the terms of that quantum is good for quantum. Also, a quantum computer would be great and actually much needed if you want to design a bigger quantum computer. Even then you need a quantum computer. Nitrogen fixation, what is the problem? To make fertilizers, to get more of your crop growing, there's a process that's called the Haber-Bosch process, but it requires high pressures and high temperatures to actually do this chemical reaction, which is called nitrogen fixation. You're basically making, what is it, NH4 or NH3, one of those. And we don't know how to do it better. It makes use of a huge amount of our natural gas, but the only way, already for 100 years, is by using this Haber-Bosch process. Very costly. We know at the same time that in the soil, bacteria and enzymes can do it under normal circumstances. Normal temperatures, no high pressures. They somehow found the trick to catalyze this reaction. We don't know how these bacteria are doing it. To go forward, actually my colleagues at Microsoft have analyzed this problem as an example problem. What kind of quantum computer do we actually need in order to solve this fertilizer problem? And this bacteria can be sort of decomposed in smaller objects, and the key element is this molecule. Back to this iron molybdenum complex molecule, which is the key molecule that makes this nitrogen fixation reaction. Somehow these bacteria know how to deal with this chemistry. We don't, but my colleagues, Matthias Streuer and colleagues, believe or estimated that you need a 200-qubit quantum computer to understand the quantum chemistry of this molecule and find out what these bacteria already know. Now, the scheme that they have set up for this calculation is, we cannot do it, but at least there's a scheme, is to make a combination of a classical computer and a quantum computer. So don't think about the quantum computer as some big machine that is a standalone machine. You can buy it. The D-Wave machine is a standalone machine. But that's probably not the way to go to do complex calculations. You can equally well do many of the tasks in a classical system and only outsource some of the calculations to the quantum computer. So the belief is that the system, as we already have now, if CPUs and GPUs and memory and what have you in your laptop, will also translate to these larger supercomputers with classical and quantum processors connected to each other. Now this is an example. If you want to know what kind of quantum computer you need to have applications, you really have to pick a particular example. There's no general theorem that says, oh, after this many qubits, it becomes useful. But if you say, I want to solve the chemistry for that particular molecule, then you can analyze it, including the gate operations, the fidelities, and everything that you need. This is one example for an application. I've just looked at press releases from various companies to see what they actually tell us that they see, the companies who actually invest in quantum computing, what they see as their motivation to develop a quantum computer. For instance, zero loss in electrical cables, probably high-TC superconductors or room temperature superconductors. Drugs development, of course, another material science problem. Electronics, machine learning, Optimization problems, could be for robotics. Big data handling, maybe that's actually related to machine learning. And also solving Navier-Stokes type nonlinear equations for airplane design. Obviously, this was Lockheed putting it in the press release. Machine learning and optimization problems was Google, etc. All the different companies that are investing in quantum computing have put out these examples as their motivation. If that all comes true, then it's amazing. And indeed, it is a revolution. It's a paradigm shift. That the world will be completely different. We will solve all energy problems, global warming, etc., as we saw in the little movie at the very beginning of this presentation. But let me add a few words of caution. Already, almost 10 years ago, Scott Aronson described in this very nice paper in Scientific American that even a quantum computer cannot solve all the problems. And maybe it's actually even a good thing as well. That if you classify the various mathematical problems in different categories, then there's this space of problems that go from, let's say, easy for anybody, even a computer, a classical computer or by hand, to very hard, unsolvable for anybody within the lifetime of the universe. And the quantum computer can efficiently solve these two sets of problems. But it becomes harder and harder, and actually we don't know whether a quantum computer is even useful if we go up to these NP non-polynomial hard problems. So not everything can be solved. And maybe it's even for the better if you're afraid about security, that we have a quantum computer and we crack all the encryption, passwords, etc. Well, just make yourself a better password, making use from these mathematical problems, and you're safe again. So when will we have the quantum computer? And yeah, that is a prediction for the future, so it's probably not correct. But if we take some assumptions, you could sort of make some assumptions and then come up with a certain graph. And I make the assumption that every 5 years, we multiply the number of qubits that we have in a circuit by 10. That's kind of a Moore's law exponential increase of the number of qubits on a chip. At the moment, at least in 2015, we had a few qubits, at least the superconducting community. 2020, 100, 1,000, etc. And there's an interesting transition point that have been announced by the Google group, that if we pass this number 50, maybe around 50, then you can do operations or set up quantum states in your quantum computer that you can no longer calculate by any classical system in the world. So there will be some kind of definition where quantum is better than classical. So you can say if you pass this threshold, we can speak of the era of quantum supremacy, right, where quantum can do things more than classical computers can do. And this threshold has to do with many different aspects, including this huge memory that you need when you want to describe or simulate a large 50 qubits circuits. Now, demonstrating quantum supremacy is nice, fundamentally important for science, but it doesn't solve any of our world problems. The problem that actually has been picked to demonstrate quantum supremacy is, an irrelevant problem for society. You need to go up. To do something useful, you probably need a number like 1 million qubits, or even more than 1 million qubits. These qubits have errors. A whole bunch of this number of qubits you actually need to reserve for error correction. So you cannot do logic on them. The only reason to be in the circuit is to correct for errors. So if you would have qubits that are free of errors, then this usefulness threshold comes down. It comes down by a factor of 100, maybe even 1,000. The overhead that you need for error corrections on qubits with an error rate of 1 in 1,000 is about 1,000 extra qubits to make one logical qubit. That's rule of thumb. Okay, there are a bunch of assumptions in this graph, but here we can do something useful. 2027, or it's about 10 years from now, one more decade. That's for solving useful questions for society. But actually, in this zone, we can already start not only building the structures, but also developing software that we can test on classical computing systems. And this is something that Microsoft has released just last week, where there's a quantum developer kit with compilers and programming language. It's called Q#, that you can use to write small quantum algorithms and check them on your laptop up to 30 qubits. And if you want to do even more, to 40 qubits, you have to buy a subscription on Azure. But I think you can start doing, or at least do your quantum classes, your teaching, and illustrate the workings of a quantum machine up to 30 qubits. And that you can do by using going online and make use of this quantum developer kit. And with this slide and actually this advertisement for the quantum developer kit, I would like to thank you very much for your attention. Thank you.
Thank you, Leo, for the very inspiring talk. We can take questions.
In your NP complete figure, the goal.
Which figure?
In the slide, you have an NP complete problem. The goal was very high, seems impossible to do. But now we know seems classical neural network can beat human. So do you have any comment here? I
don't have a comment. I think you are better. You can comment on this your own. Comment better than I can. I don't know. This graph from 2008. I'm not sure. Has it been modified by now? Yeah.
But beating human doesn't mean that it's very good. Maybe humans are very bad. So, more questions?
So, more realistically, you know that the regular quantum computer started in 1980 when David Deutsch began the formulation of that. And now it took about 30 years to come to the point here. Now, my question is how realistic you plot. What are the error bars? Curiosity. You have this very beautiful plot. I like this.
Well, there are a few assumptions in a plot, but we have a few data points as well. And this tenfold increase in every 5 years, it's not crazy. It may be 3 years, it may be 8 years. But this is, I think, the ballpark number. So that gives you this line. We know the line for quantum supremacy. And we know in one particular architecture, called the surface code architecture, how many qubits you need to solve a particular quantum chemistry problem. And actually that is more than this million. It's actually a few orders of magnitude higher than this million. But there may be other problems where you can bring it down to 1 million in that particular architecture. But the assumption of the architecture is super important because much of the overhead, many of those qubits, you actually need for error correction. And the architecture tells you how efficient error correction actually occurs. Now we have surface code, one particular architecture, and it would be great if people are smart and invent and creative to come up with an architecture which reduces this overhead. And people are making progress. I mean, many orders of magnitude are let's say the number of gate operations that we need for particular problems has been reduced by many orders of magnitude by just doing it more efficiently. If you can also do something similar for error correction, quantum error correction, this line will just come down. So this slide should also be a motivation not only to make qubits faster, faster slope, but also to bring this line down and then meet as soon as possible. Thank you.
Any more questions?
one simple question. Why the error correction requires more qubits?
You need instead of using a qubit with just a simple superposition of a 0 and 1, if errors occur, people have found a solution for correcting for errors by making bigger superpositions. So for instance, if you have 5 bits and you make it into a single qubit, then there are a lot of numbers in this 5-bit qubit. And you use half of them for the logical 0 state and the other half for the logical 1 state. So there's a lot of overhead redundancy in this qubit. But by knowing how you've constructed these two states, you can figure out that an error has occurred and you can correct for it. So there's some very interesting solution for error correction in quantum mechanics, despite the fact that you cannot copy quantum states, is by just making bigger strings to define a qubit.
Is it kind of repetitive? The measurement is a kind of. The reason why we need maybe much more qubits to do this, maybe to accommodate the kind of error correction is maybe we need more. We need to do the same thing maybe more times maybe than we can. Yeah.
Well, I don't think that more times help. But you need to encode your information with some redundancy, and that the logical qubit has more numbers in it. And instead of defining 0s and 1s, what one of the codes actually does is having a string of bits, and that the total string of bits has either a parity that is even, so an even number of 1s in it, or odd. And then if an error somewhere occurs, you also see, hey, my parity is changing. And without knowing the precise point where it has changed, you can reset the parity and correct the error. So there are some tricks that you can do by encoding the information in larger strings of data. But doing more times, it only gets worse usually.
Let me ask you maybe a silly question, but I try to be imaginative. That still about this graph. Will we, after achieving some qubits, we can construct a quantum computer with some qubits. Can we at a stage that using the quantum computer that we have developed to accelerate the process of developing better quantum computer?
I think so. Yes. And same is happening with classical IT. We need computers to make new computers. And to understand, imagine, my understanding of the quantum system stops around here. Because then it's already, so many numbers in there and you have to keep track of everything. And you need, some help, computers, whatever, to do it up to here. Above here, above this threshold, you can no longer use your laptop. So you need a quantum computer to keep track of all the information in your quantum system and how the information is being processed in your system. So yes, I think from this point on, you need a quantum computer to design your next generation. So it was not so silly.
So in your nanowire system, after you braid the Majorana, how can you measure these parity measure?
Yeah, it's super nice. So the two particles the two Majoranas are antiparticles of each other, and they either, as I said, they are a particle or they're no particle. The presence or absence of a fermion. That's what these two Majoranas actually define. And you can find out whether the two states are the presence of an electron, or I should say fermion, the presence of a fermion or the absence, by bringing them together and annihilating them. If you bring them together, or do a measurement that brings the properties together, then you either get a fermion or you get no fermion. So the measurement is done by annihilating two Majoranas. So usually you annihilate particles, antiparticles, and some radiation comes out. But this is at zero energy. There's not much energy for radiation. But there is something that's coming out. It's either a fermion or not a fermion. These are the two quantum states.
You have cited several examples of using quantum computer to repeat what classical computers have done, like solving this and that kind of problem. Can you imagine there are some new class of problems that classical computers haven't addressed? Have not addressed, and quantum computers can uniquely address?
I think the structure of space-time. I mean, there are all these ideas now coming up that even space-time has a more fundamental level that is formed by information, and in particular quantum information. That is actually entanglement of information on some surface that defines the space-time structure inside that volume. I don't know how to solve that, but if we have a quantum computer, this is my claim at Microsoft is two things. Okay, I'll make that thing, I'll make the quantum computer, but I want to own two problems. And one problem that I want to own is solve room temperature superconductivity. That was my first project as a student. And the other one is space-time. Can we actually use a quantum computer to calculate the structure of space-time based on information and entanglement?
That's Professor Wen's topic tomorrow, right?
I may need your help then. Maybe for the room temperature superconductivity as well.
Okay, last question.
Yeah, I just have a question relating to the movie at the beginning. Someone mentioned global warming as a possible application on computers. So first of all, what does it even mean to say that global warming is a computational problem rather than a political problem? I mean, related to that, once you've reduced it to a computational problem, what is the algorithm you're talking about using?
Actually, one of the examples is nitrogen fertilizer. This fertilizer problem would already say 3% of the natural gas production. So that is one of the things that you can sort of work on, at least help solving. That reduces our energy consumption of natural gases. So that would help, 3%. Room temperature superconductivity would also help. And I think there are a whole bunch of material problems that if you can solve them, it would help being more efficient and nicer to our natural environment. And I hope that is also true for climate change. But it was a little bit over the top. That's
So I think that's it for the sake of time. So
thank you.
Let's thank Professor Kouwenhoven for his very inspiring talk.